Welcome to Automated Visual Software Analytics. This part is about code instrumentation. We will introduce principles of code instrumentation and we will explain two basic forms of instrumentation: static code instrumentation and dynamic code instrumentation. Let's motivate code instrumentation. For software quality, it is a so-called low-hanging fruit of project discipline. Together with commenting and unit testing, instrumenting code is an essential technique that is used to understand system behavior and to improve software quality. What is code instrumentation? Code instrumentation refers to methods and techniques that add extra code to a computer program in order to collect, log and monitor information about program execution. Code instrumentation has manifold applications. For example, it is widely used in tools for software profiling, for software optimization, testing frameworks, error detection, memory leak detection, and virtualization. In general, there are two basic categories of code instrumentation techniques that can be distinguished: static code instrumentation techniques and dynamic code instrumentation techniques. Sometimes, and today, they are more and more combined, and this maybe could be called a third category, the hybrid code instrumentation techniques. Let's differentiate these two forms a little bit in detail. Static instrumentation techniques add extra code to the source code at compile time. The most simple way to add in a static way instrumentation code is outlined in this very short example. It's a good old assert macro in C and C++. It adds extra code that can be excluded for the product version of a software system, or it can be included and compiled for the augmented one, for the instrumented version of the software system. So in static code instrumentation techniques, we have a large range of simple manual coding techniques to automated compiler or sampler-based instrumentation code editing techniques. In the scope of dynamic instrumentation, we add extra code to the binary of a system before or even at runtime, so the binary gets edited. This way we can track dynamically linked libraries and indirect branches that are difficult to handle through static code instrumentation techniques. So that's a key difference. Static instrumentation techniques operate at compiler level, whereas dynamic instrumentation techniques operate at the binary level of a source code or of a software system. Let's start with static code instrumentation. The characteristics include that specific instrumentation source code is infiltrated, is added mostly automatically to a software system. It requires, of course, full access to the source code, and we have to rebuild the system. So the system has to be recompiled to obtain the instrumented version of the software system. The execution of the augmented system then dumps report data, the execution trace data, for example. Examples, there are many tools around, for example, Rational Test Real-Time from IBM or Atom from Digital. The principle is outlined in this diagram. We have on the left side the source code, and by code instrumentation techniques, the red parts here are inserted. This insertion process is sometimes hidden to the developer because it's done automatically. Sometimes we can also retrieve this augmented version of the source code, but the variant on the right side is that one which is compiled for the augmented system. Yes, this is just the principle of static code instrumentation, and in practice there are many variants of this principle. One example system that uses and applies and provides static code instrumentation is gprof. It's a cross-platform performance analysis tool that collects a wide array of useful function-level performance statistics from a given targeted application. gprof produces, when the augmented system is executed, by gprof we produce two key outputs. It's a so-called flat profile. It gives the total execution time spent in each function and its percentage of the total running time. Also, function call counts are reported. So the flat profile is maybe the key data that is produced by a gprof augmented system. And of course we get the textual call graph, that is data about the call dependencies. It shows for each function who called it, the parent, and who it called, so the child functions, the child subroutines. There's also a tool, gprof2dot, that converts this textual call graph data into a graphical form. Note that gprof obtains its values, its data, by a kind of statistical sampling, though it interrupts the system, the executing system, at very small time intervals, and this way it samples the functions actually executed. But this resulting data is not exact. Rather, it's a statistical approximation. Practice, this does not matter too much, but it's always an approximation and not an exact picture of the actual system behavior. But for the intended uses, such as profiling or memory leak detection, it's fine. The limitations of static code instrumentation, it increases both source code size and the size of the application binaries. Might be an issue, especially if you have embedded applications, for example, or real-time critical applications, because it also increases execution time, which may cause different system behavior. Yeah, and there's another limitation. Static code instrumentation cannot instrument external libraries, modules, or subsystems which are linked to the application under investigation. So there's a limitation. We cannot instrument everything that is that constitutes a complex system. We can only instrument these parts for which we have the source codes and for which we can recompile the system. Yeah. A different approach is taken by dynamic code instrumentation. It's based on the idea that we inject, customize analysis routines into arbitrary locations within a system binary to record a variety of performance data. Alterations can be inserted while the system is running, so the instrumentation can even change at runtime. These instrumentation alterations can be focused on relevant parts of execution timeframes in order to get highly accurate and focused statistics. Yes, it's a big advantage if we don't know in advance which parts of a system are really the interesting ones. So instead of instrumenting everything, we can focus the instrumentation on crucial and relevant parts of the system, which also helps to reduce the performance impact of instrumentation. Yeah, with dynamic code insertion, we have a breadth of behavior information, library functions that are typically loaded into the same memory space as the instrumented application. at startup time, and therefore appears just another segment of code within the binary image, can be sampled as well. So except the kernel parts, the kernel level code, it resides in an isolated memory space. Except this kernel part, we can basically instrument the whole application and get a whole behavior picture of a system execution. Examples for dynamic code instrumentation techniques include the pin tool or the Valgrind tool. Just two of many tools that are focusing on dynamic instrumentation. The principle of dynamic instrumentation or binary instrumentation techniques is outlined here. On the left, this indicates a, let's say, binary code represented by assembler statements. In this picture, represented by assembler statements, and the instrumented version at binary level, at machine code level on the right. Yeah, and sometimes this injection of instrumentation code is done at runtime, which may lead, for example, to a long startup time, because in the first or during the startup of the application, it takes a few seconds even until all parts are accordingly instrumented. But once it's injected, the application performs with a certain performance degrees, but it's not anymore affected by instrumenting certain parts. Yeah, the limitations of binary code insertion include the size. The size is increasing, application binaries get large. Execution time increases because according to the degree of injection, it may cause different system behavior because the runtime characteristic changes. A random insertion of code, for example, into a binary can also affect the flow of instructions through a processor pipeline, thus modifying the performance characteristic of the whole application. If this random principle is used, some tools use this random insertion principle. Yeah. In general, we cannot gather statistics about kernel-level code because it resides in a different memory space. And analysis and instrumentation routines created with one tool are generally incompatible with all other tools. So we always have to keep in mind compatibility issues, for example, cross-platform issues here if we start to set up code instrumentation for an application. Yeah, let's see an example. Valgrind, as already mentioned, it's an dynamic code instrumentation technique. It's actually an instrumentation framework for building different manifold dynamic analysis tools. Some tools that have been built upon Valgrind include tools for memory error detection, thread error detection, cache and branch prediction profiling, call graph generating caches, branch prediction profiling, and heap profiling. Give you just more details on Valgrind. It is especially useful to detect uninitialized memory, accessing memory after it has been freed. It can be used to assess of the end of a dynamically allocated block, inappropriate areas on the stack, memory leaks in general, uninitialized or unaddressable memory, addresses that are passed to system calls, mismatched use of malloc new and new for array data versus free delete and delete for array, and some misuses of POSIX P threads. So just collection of phenomena that Valgrind helps to detect. Yeah, this is a sample report. The heap summary, for example, says, well, there are in use at exit time still 45 bytes, so we have a memory leak here, so it definitely lost 45 bytes in a certain block. So this is one part of the report that is given back to the developer. We also see some disadvantages. Applications run approximately 20 to 50 times slower and use much more memory. And there's also an overhead tracking memory block owners, code caches. But at the end, especially if we want to analyze software systems, complex software systems, there's little reason not to use it. Use it early, use it often. So this might be a mantra for improving software quality based on code instrumentation techniques, based on execution trace data that is analyzed and evaluated by software analytics. Let's summarize this part. Code instrumentation is based on adding extra code to a computer program that aims at collecting, logging, and monitoring data about the program execution. It can observe functional aspects such as function calls, parameters, returned values, as well as data aspects such as variable values, changes to these variable values, memory allocation, deallocation, etc. Code instrumentation enables to extract information about the actual system behavior derived from and limited to the extent of sample runs. So use cases, finding appropriate use cases are very important to get a representative collection of system behavior recordings. The resulting execution trace data can be analyzed to obtain information about call graphs, control flows, test coverage, performance measures, memory consumptions and leaks, and other aspects of the system behavior. Code instrumentation serves as a key technology for software analytics to obtain information about behavioral aspects of complex software systems and related software quality aspects. Yeah, so this completes this part about code instrumentation. We have introduced a number of terminology here. Among them are code instrumentation, refers to methods and techniques that add extra code to a computer program to collect, log, and monitor information about program execution. We also introduced static code instrumentation, a category of code instrumentation that adds extra code to the source code of a software system. It takes place at compile time. And dynamic code instrumentation, another category of code instrumentations that add extra code to the binaries of a software system. So it takes place at runtime, injecting instrumentation code at runtime. As further reading, I can recommend one paper, an overview of software performance analysis tools and techniques from gprof to dtrace. I can also recommend a tutorial or information about Valgrind, PowerPoint information that outlines some of the principles underlying Valgrind. Let me end with some remarks about code instrumentation. We have seen it's an elementary technique to control, monitor, and test complex software systems with respect to the actual system behavior. So code instrumentation implements execution tracing. So to get execution trace data, we have to apply code instrumentation techniques. Dynamic code instrumentation tools show a strong technological progress in recent years. Most of them support most important programming languages and platforms. So the dynamic code instrumentation has made a large progress in the last years. As a key as a key source of information about system behavior, code instrumentation delivers key information to software analytics, such as, to name a few, module or function coverage, test coverage, system and energy for performance characteristics, and many other aspects. So in software analytics, we assume that some kind of code instrumentation is available for a given complex system in order to get more information about the behavioral aspects of that system. There's also an interesting project and framework called LLVM, it stands for Low-Level Virtual Machine. This project offers a number of instrumentation tools and evaluation tools that allow to get insight into the behavioral aspects of a software system. So you might want to have a look into this project as well.